load. Now coming to the passive elements, previously we gone with the active elements where voltage source and current source, which are ideal and practical. Now coming to passive elements, the passive elements are resistance, inductance and capacitance. The passive elements where the elements will absorb the energy or it will get the energy, but it can be either it can store it or dissipate it. So in which we'll have three elements we are going to discuss: the resistance, inductance and capacitance. Now coming to the resistance. So if any property of the material restrict the flow of electrons is called the resistance, and generally it is represented by the symbol R. This is the resistance symbol and unit of resistance is ohm. And here the resistance offered by any material when the current of 1 ampere flows between two terminals with 1 volt applied across it is nothing but ohm. According to Ohm's law, current is directly proportional to voltage and inversely proportional to the total resistance of the circuit. Now coming to the voltage current relationship with respect to power, I can write down P equal to VI. I square R, where you can represent. And next one is, if I want to find out the energy is in terms of the integration 0 to P dt, where you'll get P square R by T. So here V is the volt in terms of volt, R is in terms of ohms, and T is in seconds, W is in joules. Now, if I consider the resistance, any resistance is nothing but the directly proportional to its length and inversely proportional to the area of cross section. So the proportionality constant is rho, which is nothing but the resistivity. So the resistivity or the specific resistance. So it depends on the length of the material as well as cross sectional area of the material. Now coming to the inductance. So if any wire of certain length is twisted, then that coil, it becomes a coil, and which is a basic inductor. And if the current is passed through any inductor, the electromagnetic field is formed, and change in the magnitude of the current changes the electromagnetic field. So the unit of inductance is Henry and it is denoted by H. And when current through the coil changes, the rate of 1 ampere, changing at the rate of 1 ampere per second, induces 1 volt across the coil. So this is the symbol for the inductor, and the relation, voltage current relation for the inductor is V equal to L into di by dt. So you know that V is the voltage across the inductor, which is in terms of volts, and I is the current through the inductor in terms of amps. And you can write in different way this total equation by supplying or by applying integration on both sides, and with respect to, because when the current changing, the magnetic field is developed. So that means we need to consider the initial current also. So which is the relation, you can write it as I of t equal to 1 by L0 to dV dt I of 0, which is I of 0 is nothing but the initial current. And power absorbed by the inductor is P equal to VI, where you can write it as Li di by dt watts. And energy stored by the inductor is half Li square. Now coming to the capacitance, if I consider any two conducting surfaces separated by an insulating medium, which exhibit the property of a capacitor. So here the conducting surfaces are called electrodes and the insulating medium is called the dielectric. So generally the capacitor stores energy, likewise the inductor stores energy in the form of the magnetic field, likewise the capacitor stores energy in the form of the electric field. So which is established by the opposite charges on the two electrons. And here this electric field is represented by the lines of force between positive and negative charge, which is concentrated within the dielectric. And here the unit of capacity is farad and it is denoted by F. And the symbol for this farad is, the symbol for capacitor is F. And if I want to have the relation between the voltage current relation, then I can consider this relation, C equal to Q by V. So you can write again this also in a different way, like by considering I equal to C dV by dt, because I already know that I equal to dQ by dt. So here already Q is there, So where you can represent in a different way. Now again, if I want to modify again, and because to consider the initial voltage, so it is also the capacitor works as a storage element where it stores the energy in the form of the electric field. So you need to consider the initial voltage. For that, if I consider this relation and integrate on both sides, I'll get the relation as V of t equal to 1 by c integral 0 to t idt plus V of 0, where V of 0 is the initial voltage. Now coming to the power relation, P equal to VI, which is nothing but the VC dV by dt. And again, if I go for the energy stored by the capacitor, 0 to t P dt, so from which I will get the half CV square. Now, if I consider all the elements, 3 passive elements are there which we already discussed: resistor R, inductor L, and capacitor C. So, the resistor unit is ohms and the letter used is R. Inductor L represented and capacitor C. The unit is Henry H. Capacitor is Farad F. And if I go for the voltage current relation for each and every element, V equal to Ra for the resistor, V equal to LD by dt for the inductor, and capacitor 1 by c integral idt plus V0, where V0 is the initial voltage across the capacitor. Now coming to the current relationship, I equal to V by R, which is for the relation of a resistor, and I equal to 1 by L V dt plus I0 is the inductor current relationship, where I0 is the initial current in the inductor. I equal to C dV by dt. Now coming to power relation, I square R L by dt C dV by dt.